Okay, we I'd like to make some more comments about the solution to the random walk problem, the linear random walk on a linear lattice with a bias. There are certain points about this solution which are general in nature, and I'd like to start with that and then go on to some more properties of general birth and death processes, okay, together with hopefully some physical examples of what is happening. Now if you recall our random walk problem, so this was a random walk on a linear lattice. If you recall, we had these sites on the lattice. This was site j and this was j plus 1, j minus 1 and so on, all the way on either side over this full set of integers. And the rule of the game was that from every site j you jumped to the site j plus 1 with a mean rate which was lambda times alpha, and you jumped from j to j minus 1 with a mean rate which was lambda times beta, such that alpha plus beta is 1. And then we discovered that if you start at some arbitrary origin, say 0, the probability P of j comma t starting from the origin, this had an explicit solution, and the generating function for this was z to the j summation j equal to minus infinity to infinity, was a quantity we could evaluate explicitly, and this was e to the power e to the power lambda t times alpha z plus beta over z minus 1, and that was it. We interpreted this in two different ways. One of them was to write a birth and death equation for it and solve it using a generating function, or to say that this process, this random process j, is the difference of two Poisson processes with rates lambda alpha and lambda beta, and that immediately gave us this as the generating function. Okay. Now from this the mean values could be written down, the solution itself could be written down, etc. And just to recall to your mind what happened, this was e to the minus lambda t, and then we could write the rest as e to the 2 lambda t over 2 square root of alpha over beta times z plus square root of beta over alpha 1 over z. And that helped us immediately identify P of j comma t as a certain Bessel function, right. So this immediately gave us the solution P of j comma t starting from the origin to be equal to e to the minus lambda t, and then a Bessel function ij of 2 lambda t times square root of alpha beta, and then there was this factor alpha over beta square root to the power j, or this to the power j over 2. So that was the explicit solution, okay, right, to this probability, for this probability, okay. Now from this we can read off all the moments, etc., etc., and interpret them in some sense. For instance, the mean value j of t, this was equal to, if I call this thing the generating function f of z comma t equal to this was the generating function. The mean value here is just delta f over delta z at z equal to 1, and that follows directly from here. You differentiate this, you pull down a lambda t and then an alpha minus beta. If you put z equal to 1, this goes away, the exponent goes away, and you have this is equal to lambda t times alpha minus beta. So you see what is happening is that this bias alpha minus beta, this differential preference to the right or the left depending on alpha being bigger or smaller than beta, acts like a velocity. So this is like the mean position of displacement after time t is proportional to the time, and of course it must be multiplied by a velocity, and this drift velocity is essentially lambda times alpha minus beta. So lambda times alpha minus beta is like a drift velocity. You can now compute the mean square and so on, and we know that the variance is actually proportional to lambda t. So one should do this a little more elegantly. Instead of going on differentiating this function here, let us just find the cumulant generating function. That will solve the problem in one shot. Now the cumulant generating function, if you recall, is the log of the moment generating function, and the moment generating function, so k of u is the cumulant generating function equal to the log of the moment generating function m of u, but that was the same as f of e to the power u. And that is equal to, well, all we got to do is to take logs out here. So this is equal to lambda t times alpha e to the u plus beta e to the minus u minus 1, and that is it. Okay. Therefore, it immediately follows that the rth cumulant kr is just dr k of u over d u to the power r evaluated at u equal to 0. And what does that give us? All you got to do is to differentiate this fellow, and each time you differentiate e to the u, you get the same thing, e to the u, and you differentiate this, you get a minus or plus sign depending on whether it is even or odd. So this becomes equal to lambda t times alpha plus minus 1 to the power r beta. The first moment, first cumulant is of course the mean value itself. So it is clear that this k1 equal to j of t, and that is of course alpha minus beta, which you already derived, right. But what is interesting is that the variance is independent of this bias. So the drift is cancelled out by the fact that you subtract the square of the mean when you compute the variance from this mean square, and therefore k2 equal to the variance of j, this is equal to lambda t. This is a crucial result. It is typical of diffusive behavior. We know that the root mean square displacement must go like the square root of the time, and that is exactly what is happening here. When you compute the variance, you subtract out the systematic drift, and then you end up with precisely diffusive behavior. We can of course examine and ask whether p of j comma t itself has a limiting distribution or not. Remember, we are in an infinite lattice. Now what would you physically expect? I would expect if I start with probability 1 of being at the origin at t equal to 0, as time goes along you are spreading, you have an infinite amount of space to spread out on both sides. So although the particle is somewhere on this line, the probability of being at each particular point will go vanishing, should be vanishingly small. So you would expect it should go to 0, and there should be no stationary distribution in this problem. So in a birth and death process, when you have an infinite lattice, when this variable is not is unbounded from both sides, then the probability stationary distribution will not exist unless you put in some external condition, like you would put in a current of particles from one side and let them jump out from the other side or something like that. But that is an external condition. Without that, in general it will turn out that this probability should vanish as t tends to infinity. But that happens here, we can check that out, because it turns out that ij of whatever is inside, ij of let us call it whatever variable you want to call it, xi, whatever it is, this tends, as mod xi tends to infinity, this fellow tends to e to the power xi over square root of 2 pi xi. That is the leading behavior of the modified Bessel function, and it is independent of j, the order j, provided the order itself does not become infinite. Okay. So, if you apply that here, it is immediately clear that P of j comma t on 0 tends for long times, which means lambda t much greater than 1, tending to infinity in fact, because the time scale in the problem is set by lambda inverse, that is important to remember. This tends to e to the minus lambda t times 1 minus twice square root alpha beta, and then alpha or beta to the j over 2 divided by square root of whatever, square root of 2 pi, so that is 4 pi lambda t root of alpha beta. And this quantity vanishes exponentially rapidly in t as long as this is bigger than that. And remember that this quantity is 1 minus 2 root alpha beta equal to 1 minus 2 root alpha times 1 minus alpha, where 0 is less than alpha is less than 1. And when does this quantity become large, the largest? At alpha equal to half, because otherwise on both sides it is a parabola, it comes down on both sides. At alpha equal to half it is maximum, and then of course the 1 cancels out. So this quantity dies down exponentially as long as the coin is biased, as long as the random walk is biased. Either way we do not care, but this will exponentially vanish. On the other hand, when alpha, so P of jt 0 tends, in the case alpha equal to beta equal to half, it goes like a power law. So now this factor cancels out and it goes like 1 over square root of 4 pi 2 pi lambda t, goes like 1 over t to the half. That is typical of diffusion in one dimension linear problem. Incidentally, now that we have written this down, we can actually write down the solution to the random walk problem on an arbitrary dimensional lattice, square lattice or a hypercubic lattice or a hypercubic lattice. There is no problem at all in writing this down, because one can do this by inspection, because all the jumps are independent of each other, and then you can see what is going to happen. So let us generalize this right away, then we come back to this. So suppose I have a d-dimensional cubic lattice or hypercubic, and let us suppose that the coordinates of any point are labeled by j1, j2, jd, and let us call this the vector j. Okay. So the components are all integers and they label the lattice point. Right. I start with some arbitrary origin, it is an infinite dimensional lattice, and then suppose I put biases on both sides, which you can always do. So to move to the right there is a probability, to move to the left there is a different probability, to move up or down or move in or out and so on, right. So you can associate probabilities alpha r, beta r, where r runs from 1 to d, and the sum of all these alphas and betas is equal to 1 probably, they are all positive numbers. Then we can write down what the solution is for this quantity P of j t, given that you started at the origin. What would this be? What would this be? Because the total rate of jumps out of a site is lambda, and that is now split. Earlier it was split between lambda alpha and lambda beta on this side. Now it is split between lambda alpha 1, beta 1, alpha 2, beta 2 and so on. The whole thing adds up to 1. So what do you think will happen? What do you think will be the generalization of this? Now it is not the difference of two Poisson processes, there are several processes going on at the same time, right, and they are all independent of each other. So one can actually write this down by inspection. What do you think it will be? Well, yes, you certainly would, let us write it down here. Certainly expect this j. You would certainly have this factor as before. This comes, remember it came from the generating function because there was a you subtracted in the master equation, you subtracted minus p of j comma t with this alpha plus beta added to 1. So that produces this e to the minus lambda t, and then the rest of it is sitting here. So what you would have is simply the same thing as this, except this would be alpha r over beta r, j sub r over 2, and this would be j subscript r, alpha r beta r here, e to the minus lambda t, a product from r equal to 1 to j to d. And that is the solution. It immediately follows that this is the solution in a d-dimensional hypercubic lattice. Okay. So once again one can ask what happens if t tends to infinity, lambda t tends to much greater than 1. So this tends lambda t much greater than 1. I call this the diffusion limit. Very long time limit. What would this go to? All you have to do is to use this fact up there, and then whenever there is a bias there is going to be an exponentially damped factor. What happens if there is no bias at all? What would you expect? If there is no bias, unbiased, random walk, what would this correspond to for each alpha and beta on a hypercubic lattice? Yeah. So you have, for example, from this point you go up, you can go down, you can go this way, you can go this way, you can go into the board, you can come out of the board and so on. So there are 6 nearest neighbors in 3 dimensions. In d dimensions there are 2d nearest neighbors, right. So for an unbiased random walk, alpha r equal to beta r equal to 1 over 2d. So when you sum over all these 2d numbers you get unity. Okay. Then what would this become? These factors disappear, all these factors disappear. This factor and the exponential there cancels out exactly, and you are left with the product of these fellows, and alpha r beta r are 1 over 2d. So there is a 1 over 2d multiplying this gives you some constant, etc. But the crucial point is unbiased random walk. The crucial thing is the t dependence. And what does the t dependence do? There is this factor for each of the Bessel functions, right, and there are d such Bessel functions. So this immediately becomes proportional to 1 over t to the d over 2. Okay. So it is a power law decay, but it is proportional to 1 over t to the half d over 2, where d is the dimensionality of the space. When we solve the diffusion equation in continuous time and space, then again you will discover this Gaussian solution has a decay which is exponential, which in general is 1 over t to the, for an unbiased diffusive process it is 1 over t to the dimension over 2 in this fashion. So for one dimension it is 1 over square root of t, which is what we found just now. Okay. So you can see that there is going to be a close connection between this and the diffusion process, and we will explore that when we go to the continuous space case. But already from the random walk on a lattice one can deduce these facts. Now of course this depends, you would say, on in higher dimensions it would depend on the lattice, the nature of the lattice and what are the nearest neighbor jumps, etc., etc. But actually this feature is very general, although this solution is very specific to that kind of lattice, this is very, very general and it actually follows from much more general considerations. So we won't even get into that right now, except to say that I can go to a much more general kind of random walk. I can say that I am not on a lattice, I take steps in different directions of different lengths, they could be distributed, they could themselves be drawn from some distribution. As long as the step length has is distributed in such a way that it has a finite variance, finite first two moments, this kind of feature will always persist. These general features will persist. So it is independent of dimensionality, it is independent of the nature of the walk, etc. As long as the walk is Markovian, there is independent steps, the steps are not correlated with each other. If on the other hand you have a real material in which you have some correlation, then this whole thing goes out of the window. If for example you jump from left to right and then there is a predilection to jump back to the vacant site, back again, then of course you have correlations between different steps, all these things have to be modified. Or if you have a situation in which you remember what happened earlier and you never visit the sites you already visited once, then those have a lot of memory and they go completely outside the purview of these Markovian random walks. Okay. So the Markov assumption is very crucial here. Yeah. Yes. Okay. Now let us try to generalize this a little bit and put it in a slightly more general framework. And that is the framework of what I call birth and death processes. They have other names as well. In the semiconductor industry business they are called generation recombination processes and so on and so forth. There are different names in different areas. We will stick to this birth and death business. Now what was the fundamental assumption? The assumption here was that on a linear lattice you jumped either one step to the right or one step to the left, or in state space if J labels the states of the system, they are integer valued and then J changes by +1 or -1, this is all. If you generalize this a little bit, then once again not with any reference to a lattice or anything like that, but if I just write down the states of this system, some random variable which takes integer values, and you are at some point here, let us call it n, not let us call these sites by j once again. So here is site j, and if the process is such that you change this, the transitions occur, the W matrix I am going to write down will only connect neighboring states, then I want a model for this quantity Wkj, which if you recall was Wkj, the transition rate to go from an initial state j to a final state k. If this thing only connects neighboring states, then there has got to be something which is proportional to a Kronecker delta such that k can only be j minus 1 or j plus 1. So there is a transition probability this way and one that way from j, and all the other transition probabilities are 0. Okay. Then what is the most general thing you can have? You could have this to go such that the final state is out here with some rate, and in the random walk problem we said that is a constant rate lambda times beta, or apart from that lambda factor let me just call it beta, but this could be dependent on where you are. So as you move down these states, the rate at which it makes transitions, you still assume it goes to neighboring states on either side, but that could depend, the rate could depend on where you are, in which case this would be some beta j times this, plus the final state could be j plus 1, you could jump out there, and in deference to the random walk problem where we used alpha and beta for the bias factors, let us continue to call it alpha, but it could depend on j in this fashion. Now there are three possibilities for the state space. Either the state space which takes on integer values runs from 0 to n or 1 to n, some finite set, or it is infinite on one side, goes 0, 1, 2, 3 all the way to infinity, or it runs over the full set of integers. These three are three different classes of problems altogether, because when we write equations down with finite boundaries, then I have to change the rate equation at the boundaries to make sure that the space is confined to that range. Just as when we did the Poisson process, I said you have the rate at which the probability of 0 decays in a time t changes, that decreases with time, and then 1, 2, 3 etc., they are all functions of time. This is a Poisson distribution, but the rate equation for dp1 over dt was different from that for dp0 over dt. We will write the rate equation down once again, right. So you have to be careful about the boundaries, and then you can put all sorts of boundary conditions on it, but for the moment let us take j to be a general number, integer. Then what does the W matrix look like once you have this? Suppose j runs from 0, 1, 2, 3, in that case you would have a finite matrix of this kind if it is bounded from the other side too, otherwise it is infinite that way. And what does it typically look like? Let us look at W 1, 2 for instance. So j, so in this case k is 1 and j is 2. So this is this is beta 2, and then when k is 1 it fires. So you certainly have something here, and then you have beta 2 in this case, and this term contributes 0, okay. All the others are 0, 0, 0, blah blah etc. And what happens to 2, 1? So if you look at W 2, 1, this term does not contribute, but this contributes. K is 2, and if j is 1 it contributes a beta, and what an alpha, and what does it contribute? It contributes alpha 1, and everything else is zeros down here. And when it comes here you have a beta 3 contribution, because that could have jumped to the left on this side, and when you come here this could have an alpha 2 contribution on this side here. And what would the diagonal element be? It would of course be, we know this is equal to alpha 2 plus beta 2. This alone, because I started with 1, 2, 3, 4, labeling things with 1, 2, 3, 4, there is no state 0 here in this problem. This alone would be minus alpha 1. That would ensure that this is a stochastic matrix. The sum of each row, each column must be equal to 0, you know that. But the general structure of this matrix is a triangular matrix, so with something on the diagonal elements, negative elements, and then the super diagonal has all these beta factors, and the sub diagonal has all the alpha factors. So typically at some point in the middle on the jth column, everything is 0 till you hit a beta j and then a minus alpha j plus beta j, and then you hit an alpha j, and on the right hand side you have a beta j plus 1, because this diagonal keeps going, this diagonal keeps going, and on the left hand side you have an alpha j minus 1, etc. That is the general structure of this matrix, okay. And if there are end points to this matrix, then you got to be careful at those ends, etc. What would the rate equation correspond to in this case? What is the rate thing? Now let us get rid of this j, because that had this connotation of a lattice point, but the examples we looked at earlier, like the Poisson process, etc., we looked at a random variable n, some number n. So what would the rate equation be? So let us write that, because we are going to look at cases where n is running from 0 to capital N, or 0 to infinity, or minus infinity to infinity. And what does that look like? Corresponding to this W, the rate equation dp over dt, dpn over dt as a function of t, what is that going to be equal to? Well, it is W times this p, you write this p down in this fashion, and what is the first term that is going to appear? again you can see what is going to happen. The growth of any particular, now let us call this n. The growth of the probability here depends on fellows jumping from here and people jumping in from here, right. And whatever is jumping in from here has got to be beta, but dependent on the site n plus 1, and what is jumping in from here is alpha, dependent on the site n minus 1, right. So it is clearly alpha n minus 1 p n minus 1 of t plus beta n plus 1 p n plus 1 of t minus alpha n plus beta n. Those would be these two processes which go out. So this is alpha n beta n here, this fellow was an alpha n minus 1 and this was a beta n plus 1, so jumping in, and these two are the ones that jump out, and that is multiplied by Pn of t. That is the general equation which you have for a one-step birth and death process, in which the elementary transition probabilities only connect you from the state n to the state n plus minus 1. Okay. And these are in general functions, these rates are general functions. Okay. Apart from the fact that they are positive or non-negative, you can't say very much more. Okay. So this is the general equation. General master equation or rate equation. And we looked at special cases, of course, we looked at special cases of it. So random walk, biased random walk, alpha n equal to alpha, beta n equal to beta, alpha plus beta equal to 1. In that case, right. What about the Poisson process? What happened to the Poisson process? And incidentally, n was the element of the set of integers. What about Poisson? What did that correspond to? We had a certain rate lambda, but n now ran from 0 upwards, and the Poisson process equation was for n equal to 0, 1, 2, etc. to infinity, and in this case alpha equal to beta equal to lambda, but the process was dpn over dt equal to lambda times p n minus 1. So you had finished n minus 1 jumps in time t, and then in the time interval delta t after that you did one more with probability lambda delta t, but you might have already reached n and you are now jumping to n plus 1 decay, so therefore it is a lost term, right. So this equation was this minus Pn, and that was true for n greater than equal to 1, and for n equal to 0 you had dp 0 over dt was minus lambda p0 of t. It is clear this is a special case of this very general thing with suitable choices of alphas and betas, right. This is a pure birth process because the number n kept increasing with time, it did not ever decrease beyond a certain value. So the leftwards probabilities were all 0 and you only had increase on one side always. Incidentally, this was a stationary Poisson process, stationary in the sense that the statistical properties of the system do not change with time, which means this rate lambda does not change with time. What would have happened, by the way, we know the solution to that, right. We know completely for the Poisson process, we know that Pn of t is e to the minus lambda t to the n over n factorial, n equal to 0, 1, 2, blah blah. We know we can write down the generating function for this and compute what the coefficient of z to the n is, and that is the end of it out there. We did that explicitly. By the way, what would happen if this Poisson process was non-stationary? Suppose it turns out that for some reason lambda equal to lambda of t, and you have a non-stationary but Poisson. What would have happened to the solution? This equation is still true, because all you are saying in this entire birth and death business is, you are saying that in a time interval delta t, sufficiently small time interval delta t, either there is a transition to the left or to the right, or no transition at all. It does not say there cannot be transitions to further points, further states. It just says those are of order delta t whole squared and so on and so forth. Whereas the transition to the nearest neighbors is proportional to delta t itself, and then we got that differential equation. Okay. So now the question is, what happens if it is non-stationary? You have a nice function lambda of t, but it systematically changes with time in some deterministic fashion. What would happen to the solution? I would get exactly the same rate equations as before, except that this becomes lambda of t on this side. And the initial condition is once again at t equal to 0, n is 0. Okay. What would have happened to that solution? Well, the way we got that solution was we multiplied this by z to the power n and summed over n to write the generating function down, right? And we got an equation which said essentially delta f of z comma t over delta t was equal to lambda times z minus 1 f of z comma t. We got a z because there is an n minus 1 here. So when you multiply by z to the n, you got to remove a z and write it as z to the n minus 1 and sum. Okay. So that is how the z came out. Now what is going to happen is this. Once again, the boundary condition is, initial condition is the same as before. We know that only P0 has a value at t equal to 0, that is 1. So f of z comma 0 equal to 1. This is the initial condition. What is the solution to this equation with that initial condition? This is not a constant. It is not a constant. So how do you solve, what is the solution? Yeah? Yeah. It is e to the power z minus 1 integral from 0 to t dt prime lambda of t prime. That is it. Okay. You have to integrate both sides. A separation of variables immediately gives you this solution. Okay. That is the general solution. In the case when lambda is constant, that exponent becomes lambda t, as you can see. Okay. And it satisfies the boundary conditions. We got a unique solution. Right. So if you define this quantity, you define this to be some lambda of t, call it that, then we are ready to write down what the probability density probability itself is. Once again it is just the coefficient of z to the power n. So you would get exactly the same solution, except that you now have e to the minus lambda of t to the power n over n factor, and that is it. Okay. So this particular making it non-stationary is quite trivial. It is quite trivial. You get the solution immediately. Okay. This occurs in the problem of what is called time dependent short noise, okay. But it is a trivial extension of the original Poisson process. Okay. What is much harder to do is solving the general equation, this equation here. This is not at all a trivial matter, even though it is a one step process in which you only go from n to n minus 1 or n plus 1. Even then, if these coefficients are sufficiently independent in a complicated way, then writing down an explicit solution is out of the question for this set of coupled differential equations. Okay. Constant, no problem. That was a biased random walk problem when alphas and betas are independent. Well, the next thing you would guess after that, which is solvable, would be to say, suppose these are dependent on n linearly. Okay. That would be the next natural thing to do linearly. For instance, there is a physical problem in which you have a quantum mechanical harmonic oscillator, say levels are all quantized, and let us suppose it is put bathed in radiation of the right frequency, so that the oscillator can absorb a photon, go to one state higher than it, or it can emit a photon of the same frequency and go to a state lower, right. And then you ask, what is the population probability of population of the state n of this oscillator. That problem would be exactly this kind of rate equation in which the alphas and betas are linearly dependent on n. In fact, that is how Einstein actually derived, that is how Planck originally got the Planck law. In that case, what happened was, for the radiation problem, turns out that alpha n plus 1 equal to some constant times n, and beta n equal to some other constant b times n. Alpha n minus 1 was proportional to n, and beta n was proportional to n once again with some constants a and b. Okay. I am going to leave it as an exercise for you to solve this set of differential equations given this. Not altogether trivial, but at least find the stationary distribution. In this problem, n runs 0, 1, 2, 3 up to infinity. They label the levels of the harmonic oscillator, right. So, n is and find Pn stationary. I will give the answer too. It is a geometric distribution which depends on the ratio A over B. Okay. So, try to derive that. What you have to do is to put this in and then equate this, put P stationary here everywhere, no T dependence, and then equate it to 0. Okay. And then you try to find out what the stationary distribution is in this case. But actually, when you have a linear process, you can go a little further, and that is interesting because this rate equation can give you some physical information, and here is how it happens. Let us suppose, for ease of algebra, let us suppose for a moment that n runs over all the integers, so that I do not have to worry about these boundary points, otherwise I have to be very careful about the boundary conditions and put in appropriate conditions each time. I might, for example, if n runs from 0 to infinity, I will have to define alpha minus 1, beta minus 1 as identically 0, put in a formal beta and define it to be 0 and so on. But let us just say that n runs over all integers, suppose n element of z. I look at this and I ask, what is the average value of this random variable n at any time t? So, what I need to do is to compute n of t. This is equal to summation over n times Pn of t over all the integers. Since I am summing over all integers, whether the summation index is n or n plus 1 or n minus 1 does not matter, it is over the same set. I am going to freely shift things. Okay. Then what happens to this? What is d over dt of n of t equal to? I multiply both sides by n and sum over n over all the integers. Then the first term gives me an n, but I make it an n minus 1, and remember to add that one later on. So, it is going to be a summation n minus 1 alpha n minus 1 p n minus 1 plus summation. Now, in this fellow here I multiply by n, so I make it n plus 1 and subtract the n later on. So, summation n plus 1 beta n plus 1 p n plus 1 minus summation n alpha n p n minus summation n beta n p n, and then let us be careful, I multiplied by n, I wrote it as n minus 1, so I got to add, so there is a plus, I add 1, so this is summation alpha n minus 1 p n minus 1, and then I have to subtract this fellow here, no, I had an n, I wrote it as n minus 1 plus 1, I had an n, I wrote it as n plus 1, so I subtract 1. So, minus summation beta n plus 1 p n plus 1, okay. And this is over all n, but I can shift the summation index to n minus 1 and it is over the same range, and this term cancels this and this term cancels this completely, right. So, we have an interesting result which says I do not care what these coefficients are, but if they are linear, whatever they be, I do not care, there is an equation which says d over dt, the average value of n of t, is equal to this quantity and that quantity. But what is this equal to? Again I can translate the summation index to n, but I am got the weighted average of alpha sub n, whatever function of n that be. So, this is equal to alpha sub n plus beta sub n. Okay. So, I have an equation actually, pardon me, a minus. That equation could be nonlinear in n. In general it could be complicated, etc. So, it is not trivial to solve it, but you have an explicit equation for the average value in terms of possibly higher moments in general, but you have an equation. Similarly, if I multiply by n squared and compute what is n squared of t here, again this thing is equal to n squared p n, and the trick is exactly the same as before. Write it as n minus 1 squared and n plus 1 squared, shift it, and that will cancel against these fellows here, but there was a 2n plus 1 which you added, you must subtract those fellows out, add or subtract those guys out. But remember, each time whenever these fellows are n minus 1, you better match that here. So, in the linear terms you got to be careful once again, subtract, etc., and you get a closed equation once again, an equation in terms of average values. So, in this case I do not remember what it is, but one can work this out. On the right hand side you are going to get things like average value of n times alpha n plus beta n, and then there is possibly an alpha n minus beta n, etc., plus something times this, maybe there is a 2 here because there was a 2, remember, each time, etc. So, these factors can be worked out, but this is the sort of equation that you would get. Okay. Now, tell me, if the process is linear in n, what is the special feature that emerges at once? Suppose the alphas and betas are at best linear in n, each of them is some constant times n plus some other constant. What happens then to these two equations? Sorry, this is d over dt. Yes. What happens then? What is the special feature that emerges? Well, this fellow is also linear in n. So at best it is going to involve this guy. So you get a closed equation for it right away, which you can in principle solve. Okay. And then what happens here? Again the worst you get is a quadratic in n, the average value. So this set of equations is closed completely and you can solve it. Even if you are not able to solve the full time dependent problem for p of n comma t, you can still solve the equation explicitly for the average value as a function of t and the variance completely, provided the process is linear, provided the coefficients are linear. So when I say the whole differential equation, these are linear equations in the p's, no doubt about that, but when I say linear, non-linear, etc., I mean these coefficients. If they are linear in n or non-linear in n, you have a big difference. If they are linear, then not only do you get a closed set of equations for the a's, for the mean and the variance, but you can also solve these equations explicitly. But if it is non-linear, then it depends, changes from problem to problem. Okay. I will give some physical examples of this next time, but you have already seen that the simplest of cases, like the random walk problem and everything that is mapped onto the random walk problem, these coefficients are constant, and then when it is linear you have the radiation is an example of this. Chemical reactions would have similar kinds of rate equations, etc. Okay. A very interesting question is the existence of a stationary distribution, and the rule was, and we saw already explicitly that in the random walk problem there is no stationary distribution because J ran from minus infinity to infinity. But when you have finite boundaries, you physically expect there would be a stationary distribution unless these boundaries are absorbing boundaries, they cause the system to disappear, and we will give examples of that as we go along. Okay. So let me stop here today and take it up tomorrow.